Welcome to yet another class. I'm Dr. B, your chemistry teacher online, and today we are going to look at the Beer-Lambert law. We're going to look at the Beer-Lambert, the Beer-Lambert equation. Okay, the Beer-Lambert equation. That's what we are going to be looking at today, Beer-Lambert equation. Now, as usual, looking at this Beer-Lambert equation, do not forget to share this class. It's very important that your friends, your colleagues be part of what we are doing here. Do not forget to share. Do not forget also to like, comment, and in my Facebook page, Dr. B Chemistry class or Dr. B Science classes, also do well to share, to follow, and let your friends know that they can also follow and subscribe so that they can always have these lectures as they drop. Don't forget also to drop your comments and then your likes. Thank you very much. Now let us look at the Beer-Lambert law. The Beer-Lambert law is an extension of the UV visible spectrophotometer. Remember that we had discussed the UV visible spectrophotometer or spectroscopy, as you may wish to call it. And we're talking about absorption of the UV radiations, okay, by a sample or by substance. We also discussed the principle, the application, and the instrumentation. Go to my former classes, lectures, you are going to see all those things there. Now, today we are going to look at the Beer-Lambert law or the Beer-Lambert equation. It's important for us to put down something to explain what this means. And we're going to, by extension, derive that equation in a very simple way. All you need to do is to pay attention. Now, if you have something of this nature, let's say you have a light source, okay, and then, you know, I won't want to start drawing the instrumentation again, we have it already, but let's say we have an abridged instrumentation, and this light source links to a sample container and goes out to a detector, a detector. Let's say it goes out to a detector, and then this is your detector, okay, and then we have this. Now let's say this is your monochromatic light source, and this is your sample container, and this is your detector. Let's say we have this. Okay, now in this sample container you have a sample in it. What the Beer-Lambert law said is simple. Now it's important for me to let us know that there is the Lambert law and there is the Beer's law, and that the Lambert law and the Beer's law discuss something almost the same. The quantitative explanation or description of the UV visible radiation instrumentation from the Beer's law and the Lambert law, it's almost the same. And that is why both laws were collapsed by both of them to form the Beer-Lambert law, and I'm going to tell us why. Now, if you look at the light source, what Beer-Lambert says is simple, that when you are given a monochromatic light source, for example, remember that there is going to be a ray of light that is going to go in, because that beam of light that came from the original light source that comes through the monochromator will be narrowed into the required light, the ray of light that is going to hit this based on the wavelength of the light that this particular sample will require. Now, when this light comes in here is described as IO, and this is simply the intensity of the incident radiation. So the intensity of the incident radiation that leaves the monochromatic light source comes into the sample container. This sample container is controlled by two basic things. One is the concentration of the sample, and the other one is the path length. In some places, this can be written as X. So what happens around this sample container is the concentration of this particular sample matters, and then the path length of the container to which it is being used or housing this sample also matters. Now, when this incident radiation hits this particular sample, three things happen. One is that there is going to be absorption radiations. Okay, so there will be radiations that will be absorbed. There will be radiations that will be absorbed. There will also be radiations here that will be scattered. And there will be radiations here that will be reflected. That is what you must know. That from a monochromatic light source, once there is incident radiation hitting the sample container, three things happen there. One is that there will be absorbed radiation, there will be scattered radiation, there will be reflected radiations. But the one that is of most importance is the absorbed radiations. So the sample is going to absorb radiations. Of course, you do not expect the extent of radiation that was incident on this sample to be the same that is going out. So you rather have a reduced radiation at this point that is going to the detector. This reduced radiation is because of what? Of the absorbed radiations by the sample. Once the incident radiation hits the sample, some of these radiations at that wavelength will be absorbed. So you have a reduction in the transmitted radiation that is going to hit the detector, where you can possibly do what? Possibly measure the intensity. And what Beers and Lambert law says that make these two collapse their laws is that both of them believe that the reduced radiation, which is the transmitted radiation, depends on the concentration of the sample and also on the path length of what the sample container. Since both of them believe that there is a reduced radiation, which is the transmitted radiation, and that depends on the concentration of the sample and the path length of the sample container, both of them understood the fact that they were saying one and the same thing, and there was need for their laws to be collapsed. And that is why the Beer-Lambert law came up and the Beer-Lambert equation also came up. So with this, we have the intensity of incident radiation, intensity of transmitted radiation, we have the concentration of the sample and the path length of the sample container. I'm sure we have a little understanding of where the Beer-Lambert equation or law is coming from. Now let us look at how we can derive the Beer-Lambert equation in a very simple way. So you just need to pay attention and work with me. Alright. Let's see how we can derive the Beer-Lambert law, or the Beer-Lambert equation rather. Now, since Beer-Lambert believed that the intensity of what the transmitted radiation, which is reduced, depends on the sample container and also depends on the path length of the sample container and also on the concentration. Their equation was derived from that relationship. And that is why we have I equals to what? Equals to IO exponential this. Now, here is the incident, this is the transmitted radiation equals to the incident radiation, intensity of the incident radiation to the exponent of minus this. This is simply known as the molar absorptivity coefficient, okay? Where you see it's written, this is molar absorptivity coefficient. Molar absorptivity coefficient, where C is the concentration, C is the concentration of the sample, and your X, which can also be written as L in some books, is simply the path length. The path length. Now, of course, path length is measured in centimeter. So if you are carry out any calculation using the Beer-Lambert equation, you must make sure that the path length is converted to centimeter. Otherwise, your answer is wrong. And the concentration is always measured in mole per liter, while the molar absorptive coefficient is measured in liter per mole per centimeter. So these units are very cardinal. If you are carrying out any calculation, you must ensure that there is a conversion to the proper units before you use the Lambert equation in doing your calculations. Now that is just by the way. Now if we have this equation, originally the absorbed radiation is given as the transmitted radiation minus the incident radiation minus the transmitted radiation. Okay, so the absorbed radiation, intensity of absorbed radiation is equals to the intensity of the incident radiation minus that of the transmitted radiation. Of course, you know that incident radiations are higher than those of the transmitted radiations. This is, like I said, because of the reduction in terms of absorption of incident radiations by the sample, which depends on the concentration. Now, if this is true, we are going to do what? Substitute this equation for this. We'll substitute this. That means we'll put this equation to take this one. So in that case, it means that we'll have the intensity of absorbed radiation equals to IO minus, we'll bring in this to take this. So that is IO to the exponent of minus this Cx. This means that we now have, remember that it means that your intensity of absorbed radiation is equals to what? The intensity of incident radiation times this, minus this. Now, in mathematics, just note that in mathematics, when you have A minus AX, you can rewrite this equation as A bracket 1 minus AX. This is because of course you will know that, or rather 1 minus x, but let me not, 1 minus x. Now this is because A times 1 is A and A times x is AX. So if we apply what we have just done here to this equation, what we're going to have will be what? IO out in parentheses 1 minus this. That's what we're going to have. So with that, we are going to build our equation 4 on that. So that means we are now going to have I absorb equals to what? Equals to IO bracket 1 minus exponent of this. This is our equation 4. Following what we have done here. So we're going to have this. 1 times this times 1 will give you IO, and then this times this will give you IO and that. Now, at this point, we can simply make this the subject of the formula. Now, to make the subject of the formula, we are going to bring this beneath here. So, we'll have this all over IO equals to 1 minus E Cx. This will give us equation 5. Now, 1 minus this, the whole of this is greater than 1. So 1 minus this will still give you a negative sign. Okay, so in that way, we can still write the equation as this over IO equals to what? Minus E exponent C this. This gives us equation 6. Okay, now with this equation, what we simply need to do here is to remove this away. And when we remove this, we'll introduce the logarithm sign. So we'll look at that. So we're going to introduce the logarithm sign by simply say log of IABS all over IO is equals to minus this. Now this equation 7 can also be related to absorption. That is to say, if you were calculating absorbance, this is also what you can use for your absorbance, because log of the intensity of absorbed radiation over the intensity of visible radiation is equals to absorbance. Okay, now at this point, what we simply need to do here is to do what? Is to introduce the natural logarithm. So we do what? We introduce natural log. Remember that natural log is to base 10. Natural log is to base 10. So if we introduce the natural log, which is to base 10, this equation 7 will now be written. The equation 7 will now be written as log base 10 I absorbance over IO is equals to what? Minus this. That's what we have. What we just did is to introduce a natural log. We just put 10 here. And if this is true, we can possibly do what? Remove the natural log for this side of the equation. And that is going to give us I absorbance over IO equals to what? 10 raised to the power minus this. And finally, we are looking for the what? Intensity of absorbed radiation. So the intensity of absorbed radiation will be equals to IO 10 raised to the power minus ECX. And this is the Beer-Lambert law or equation. This is the Beer-Lambert equation. So you can derive your Beer-Lambert equation in this format. It is still very correct. But always remember that the Beer-Lambert equation is used to determine absorbance and intensity of radiations. So absorbance is equals to this and is equals to the log of I over IO. Always know that. And do not forget that I said, whenever you are doing your calculation using the Lambert equation, it is necessary to do your conversion. Make sure that the units are correct and in alliance with the Lambert equation. Now, that is all we are going to discuss today about the derivation of the Lambert equation. Please do not forget to share this class. When you share it, don't forget to tell your friends to subscribe, so that as we continue, they are going to have those lectures just appearing on their phones and screens. Don't forget to like, send your comments, even their questions. Don't forget also to to follow at my Facebook page, and we'll continue to make this class available to us. I'm still your Dr. B.